folks, we started to talk about changing momentum and changing energy. All right, we're going to focus on the momentum part for today, and people in my classes have gone through an exercise to lead you into this. This is a review for some and maybe new for others. So here's an object, okay? And this object, let's say, is under the influence of a single constant force, and I'll represent it as a force F. All right. Maybe we're saying that this is like one of our little battery-powered hovercrafts where we can get rid of friction and there's only one force acting on this. We had in our little lab today, we had a cart with pretty low friction axles and the bearings, and we have a fan that mounts in the back of this thing, whoosh, 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 right? And this thing does that. So yeah, so we're simplifying. Here's our object, our little red circle there. All right, so what happens, right? What happens when this object experiences a single constant force? Well, there's a couple things you can say. One of them is that velocity changes. All right, this thing speeds up. If it started from rest, let's assume it starts from rest, this thing speeds up. All right, now, more so than that, we can talk about specifically how the object speeds up. So a lot of us today, a lot of my dudes looked at how velocity changes as a function of time, right? And you saw that this graph was linear. And linear graphs tell a very important story, all right? And the important story is that we can say V changes at a constant rate. Right? When we talk about how things happen over the process of the passage of time, as physicists or scientists, we talk about that as the rate at which things happen. And if there's the same exact amount, check this out. There's the same. Let's take an arbitrary amount of time. There's an arbitrary amount of time. Well, in that amount of time, velocity changed by that much. Here's a delta V. All right. If you then look at any other equal amount of time, any other equal amount of time, and look at how much velocity changed during that amount of time, again, the same amount of time, but later on, well, look what you get. You get the same delta V. So in every equal amount of time, you get the same change in something else. That's what changing at a constant rate means. Well, that's all well and good, all right, but what we're interested in is momentum. Well, saying velocity is sort of like saying momentum, at least because we're talking about an object of a certain single mass, all right? And so therefore, we can say this, maybe more importantly, that momentum changes at a constant rate. Fair enough? In this case, momentum happens to increase in magnitude. When I say increase in magnitude, I mean starts at 0, I guess, because we said starts from rest, ends at some bigger value. Now notice, this isn't a graph of momentum, it's a graph of velocity as a function of time, but since momentum is m times v, if we just did, well, multiply mass times whatever is on our y-axis, then now we have momentum. Okay? So, now notice, I said changes here. Momentum changes at a constant rate. When I read a lot of things today, people said momentum increases at a constant rate. That's true. In this case, it does. Well, let's think about or look at another case. Let's talk about an object that was sliding across the floor to the right with an initial speed v. Right. So watch this. If I grab this object, right, I got it here, and I slide it. Yeah, That's what it would do, right? We're not saying, this is not one of our hovercraft. This is a book on the floor, and I slide it. Then what does it do? It does that. It comes to a stop. All right? So why does that happen? Is it back here anywhere? So if this thing had some initial speed v, let's say, yeah, it's got some initial speed this way v, which is not a force, by the way. Velocity is not a force. Well, this thing slows down because there was a force that pointed back that way. All right? There was actually, I call it a friction force that pointed back that way. And so this object's, well, if we look at a graph of, in this case, momentum as a function of time, hey now, if we look at momentum as a function of time, this would do something, well, like this. We'd still get a constant rate of change of momentum, but this thing would end with a momentum of 0 if we let time go long enough. So again, we get that momentum. No, yes, good. We get that again, momentum changes at a constant rate. All right, so that's what happens when objects are under the influence of a single force. Their momentum changes at a constant rate. The momentum changes by the same amount during every equal interval of time. All right, in this case, we could say that the object loses, well, let's see. There's two ways we can say this. All right, so we can say that our object, one, we could say, well, if we said this was the positive direction, and it had some momentum in the beginning, and now it doesn't have any momentum, we could say it lost momentum to the right, which is the same thing as it gained momentum to the left. Those are the same thing. And notice the force is to the left. So that force causes that change in momentum. In our previous case, we have that this object clearly, hopefully clearly speeds up, right? We have a force to the right, and this thing gains momentum to the right, which, yeah, means it speeds up to the right. Okay, so we have a force this way and gain momentum that way. So now let's try to make some connections. And the connection we've got to try to make is, what is it we can actually say about a force? I mean, all right, so we know that, we know this is true, that a force causes this, or this, or this, or anything linear a force can cause. Any constant rate of change in momentum a force can cause. All right, but let's think a little more about, what does that mean about force? Well, I'm going to start by saying, let me get rid of this stuff. Let's actually look at this graph of momentum versus time. Our graph that has a nice constant slope. All right, well, remember, momentum is measured, right? Momentum is m times v, kilograms, meters per second, right? Time measured in seconds. The slope of this line, that by definition is, you know, a rise over a run thing, is, well, is a delta p over a delta t, or the rate of change of momentum. right? This, I would say, this I call, here's rate of, anytime I see per unit time, to me that means rate of, and the top is change of momentum. All right, so the slope is the rate of change of momentum. Okay, it's measured in, check this out, the delta P in kilogram meters per second, the delta T in seconds, right? So that means the slope, kilogram meters per second divided by seconds, is the same as multiplied by the reciprocal of seconds, right? The slope is measured in kilogram meters per second squared. Now, we've talked about some different kinds of units, and some of them look like this, and the one that looks kind of like this is energy, right? Energy, remember, like we can do like UG, right, is mgh. Well, mass in kilograms, G in newtons per kilogram, H in meters, which says, well, we know that UG is measured in joules. It says that a joule is a newton meter, right? Well, we also know that we got like K 1/2 mv squared. All right, so that's mass in kilograms. V in meters per second, but it's squared, so I got to do that. So a joule is also a kilogram meter squared per second squared, right? We'll check this out. Come here, you. We take these two. They're both joules. A newton meter is a kilogram meter squared per second squared, right? Well, I got a factor, a factor of m that I can divide out of both sides. And look what we get. Kilogram meter per second squared. Apparently that's a newton. And what's a newton? Well, a newton is a measure of force. So what we get here is that the slope of this graph is the rate of change of momentum. It is delta P over delta T. The units of that turn out to be units of force, which means that delta P over delta T is a force. And maybe this isn't a surprise because we've been saying that a force causes these constant rates of change of momentum. But it's not only that force causes the rate of change of momentum, force is the rate of change of momentum. All right, so by definition, force is delta P over delta T. I put those vector symbols there because the direction of a force is always the same as the direction of the change in momentum that it causes. All right, just want to sort of review this. Right, we spent some time saying, or looking at, all right, we got a single force. What does that do? Well, it changes momentum at a constant rate. People have gotten most of the kids that I worked with today got pretty comfortable with that. That force causes that momentum to change at a constant rate. All right, so it causes that. Here's another case where we said it could cause a different looking change in momentum, a loss of momentum, right? But it's not only that the force causes the constant rate of change of momentum, it's that the force is, come on now. It's that the force is equivalent to the rate of change in momentum. And how do I know that? I know that by looking at the slope of this graph and what the units of that slope happen to be, and then sort of diagnosing, well, that looks something like what these joules were, but that's a newton meter and this thing, and set those equal in a newton. I mean, hopefully we know that force is measured in newtons, like we would say spring force, right? That's measured in newtons. So a newton happens to be equal to these units, and that's the units of our slope. So that means that the slope is a force. All right, so that's a expression that's pretty fundamental. You'll see different forms of this expression, but that's an expression that's pretty fundamental to how a lot of stuff works. I mean, really, like the fact that this simple equation that if we know how much force is applied to something and for how long, we can tell how much its momentum changes. Now, within momentum lives a couple of things, mass and velocity, so, we can pick those apart, but this is a very profound statement. It doesn't look too profound, it looks pretty simple. That's one thing that's awesome about physics, is some of the most profound statements are very simple in their structure. It's called elegance. So let's use this and say, what impulse? Impulse. Okay, so here's an idea, or a term. Impulse, by definition, is change in momentum. We just give it a different name. Impulse means change in momentum. So impulse, well, we call that J for some reason, right? And J, by definition, is delta P. All right, so just get used to that terminology. When you see the word impulse, it means change in momentum. All right, so let's define a baseline case and say, well, what impulse does an object experience? Well, first of all, that depends. What change in momentum will an object experience? Well, that depends. It depends on a couple of things. Let's go back to our definition of force. Our new definition of force is that force is the rate of change of momentum. I guess you could say the rate of impulse. Okay, I don't know if that's as common a phrase, but look, this says that how much will an object's momentum change? Well, that depends. Just algebraically rewriting, we get there. How much does an object, how much will an object's momentum change? How much impulse does an object experience? Same question. Well, it depends. It depends on two things, right? It depends on how hard do you push it? For how long do you push it? Right? And if we say there's a force F, and let's say applied for time capital T, well, we've just defined that this object experiences an impulse J, which by definition is its change in momentum. Well, and that would just be Ft for us, right? Ft. So let's compare some other cases to that. Like, for example, now this, you know what, doesn't matter yet. Let's say that here's one that gets a force F over 3, but let's say it's applied for twice as long. Well, how much does this object's momentum change compared to the baseline case? Well, this J would be, well, generically delta P, generically F delta T. So this force is F over 3. Our delta T is 2T, so that gives us 2F over 2FT over 3. Well, how's that compare to our initial case, right? Our initial case was Ft. This is 2/3 Ft. So I'll say the impulse in case A is 2/3 of this impulse. Yeah, good. What about if we did this? Let me shrink this stuff up. Group. Let's say in this case that we do, well, how about a force like this? Let's make it 2F. and let's say this is applied for a long time, 3 times as much time. Well, this J in case B is the change in momentum is F, we'll call it B times delta T. B is 2F times 3T, and that's 6FT. So, well, remember, our regular old baseline case was FT. This is 6FT, so this case is 6 times the baseline. This object's momentum will change 6 times more than the other objects will. All right. Case C, I'm just going to skip because how many of these can you do before you get bored with it? All right, but what I am trying to show in case C is, wait a minute, but this one looks bigger, right? What if this is like a mass M and this is like a mass 4M, right? Well, okay, how about this? So we got this 4M thing, right? But let's apply a force F, and let's apply for time T. Well, how much does this object's momentum change? Well, J in C is F in C times delta T in C. Well, that's F times T. So J in C is the same as our baseline J. These things have the same change in momentum. But this one's 4 times as massive. Well, so what? It doesn't matter. Now, will something be different? Yeah, something will be different, but not the amount of momentum change, not the amount of impulse. Since their masses are different, you might be able to think of what might be different in the end about the object's motion, but it's not how much their momentum changes. Okay? Okay. Let's talk about a application of this idea. Yikes. A car hits a tree. Yeah, impulse and automotive safety. All right, there are lots of different engineering applications of this idea that force, by definition, is the rate of change of momentum, or that delta P is F times delta T. So here's the deal. Imagine a car hits a tree. It's not, everything's fine. It's the passenger is one of those crash test dummies. Yeah, right. So let's see. We want to talk about what's the benefit of having an airbag, right? 2 options. Either crash test dummy hits a steering wheel and comes to a stop, or a crash test dummy hits an airbag and comes to a stop. But guess what? Either way, stops. Stops. So if we say, in terms of momentum and time, momentum and time, in each case, it's the same crash test dummy, the same mass, and we'll say that in both of these cases, the car was going the same speed in the beginning and still comes to a stop. So if the car was moving at the same speed in each case, and the crash test dummy is the crash test dummy, then the initial momentum is the same in each case. Yeah? So here's what happens. Crash test dummy hits the steering wheel. And guess what? The stop and the change of momentum happens real fast. Let me undo because that's ugly. Happens real fast. Maybe like that. Except it doesn't go below 0. In the case of crash test dummy hitting the airbag, maybe this happens. Right? It takes longer for the stopping to happen. All right? What's the same in each case? They both start with the same, they both start with the same initial momentum, and they both end up with the same final momentum of nothing. So in each case, same delta P, same impulse. What's the difference? The difference is the amount of time, and that has a huge, I don't want to say impact, it has a huge impact on the relative safety of each case. And why is that? Well, the answer lives right here, right? If we want to get the same impulse, it can happen in lots of ways, because force can be applied for lots of different amounts of time, right? In the case on the left, to get a certain impulse, delta P, what we get is a relatively short amount of time, which means a relatively big force is required. Over here, we get the same delta P, but we extend the amount of time, a relatively large amount of time. Well, that can require a relatively small amount of force. And small amount of force is good if it's being applied to your face or a crash test dummy space. Okay? Now, how else can we look at this? We can look at this in terms of what force looks like as a function of time. So what I want you to try to sketch very qualitatively is what force might look like as a function of time in each of these cases. There's a difference. I'll give you a hint. This one lasts that long. This one lasts this long. So we'll talk about these graphs. We'll start to talk a bunch about these graphs of force as a function of time and what we can tell from that. All right, one of the big deals is you got to be okay with that this graph of momentum versus time, the slope is force. All right, these graphs of force versus time, we're going to get a lot of practice with and use those to find something else in a different way. Okay? So, that's it, folks. See you soon.